So in the first video for 6.2, what we're going to be doing is finding something called the inverse of either a function or a relation. So we've learned about functions. Relations are similar. They're just kind of how x values relate to y values. So the definition of inverses, we're going to write that right under this first bullet point here. An inverse relation is a set of ordered pairs obtained by exchanging the coordinates of each ordered pair. Okay, so exchanging the coordinates of each ordered pair, what that means is that the x values trade with the y values. So what used to be the domain becomes the range, what used to be the range becomes the domain. So we've got these ordered pairs right here. It says they're the coordinates of the vertices of a rectangle. Find the inverse of this relation. Okay, so the inverse, we are literally just going to take the ordered pairs and we're going to swap them all. So instead of 1, 3, we're going to swap them and they're going to become 3, 1. And the second ordered pair is going to do the exact same thing. Swap the 3 and the 6. Swap the 0 and 6. Swap the 0 and 1. So that's literally what we did, is we exchanged the coordinates of each ordered pair. We formed an inverse with functions. So some properties that we can write down right here. And this is basically what we had on the previous page. If f of a equals b, meaning if you have the original function, you plug in a, you get b, then we can write the following. So here's our notation for inverse. We write f with a little -1 like that. So it's not an exponent. That right there stands for the inverse. So whenever you see this little -1, that means we're talking about an inverse function. So since all of the x, y points exchange, that means if we plug b into the inverse function, we get a. So it's basically what I had written on the previous page, just kind of in a different way. Okay, horizontal line test. We've learned about the vertical line test before. The horizontal line test is what tells us whether a function has an inverse or not. Okay, so the horizontal line test can be used to determine whether the inverse is also a function. Okay, so okay, so let me show you what I mean. So let's start with just like a really simple parabola like this. Looks like that. And if we take the inverse, we're rotating it. And so what it ends up looking like is this. The inverse rotates 90 degrees and it looks like that. And what they're always doing actually is they're rotating around this line right here. And you can see that with the rectangle. If we put this line kind of straight down the middle, they're rotating over that line. Goes from here, rotates over the line, starts out here, rotates over the line and ends here, or it could start here, rotate over the line and end here. So that's exactly what our parabola is doing. Starts right here, we rotate it over this line, and it ends up right here. So if you're looking at our original function, this is a function. It would pass the vertical line test, but if we tried to apply the vertical line test to our new function, this is not a function. The inverse is not a function, and that's because it failed the vertical line test. Well, if we looked at our original function, we could have seen that our original function wasn't going to pass the horizontal line test. Okay, so this function right here failed the horizontal line test. I'll abbreviate. So because this one failed the horizontal line test, when I rotated it, this one failed the vertical line test. Okay, so since this one fails the horizontal line test, that means my inverse is not a function. If a function passes the horizontal line test, that means the inverse would also be a function. All right, so last thing I want to do in this video is find actual inverse functions. And what we do is we exchange the domain and range. Okay, so this one we don't have an individual set of x and y values, so we're literally going to swap x and y, rewrite the function. Okay, so first of all, this function, whenever I see an f of x, I can always write it as a y. Okay, so we can rewrite it like that if that's going to help you out. So like I said, on the fronts, on these ordered pairs, we literally took this x and this y and swapped them. This x and this y and swapped them, etc. So what we're going to do in the equation is literally swap the x and the y. So when we go to solve our inverse function, we start by exchanging x and y. Okay, so exchanging x and y is the first step in finding an inverse. So instead of y here, I'm going to write x, negative 1/2, and instead of x, I'll write y. And then what you do is whatever algebra you need to do to solve the equation for y. Okay, so we want to get it to a point where y is by itself again. So here we could subtract 1 from both sides. So we lose it over here. We've got x minus 1 equals negative 1/2 times y. All right, and then the next thing that we would do, we want to get rid of this negative 1/2. So we can multiply by negative 2, because these things would actually cancel each other out. They would just multiply to 1. So I would do the same thing over here. Multiply both sides by negative 2. So I can distribute that negative 2. I will have negative 2x plus 2 equals y. So that's my inverse. The way I want to write it is with this notation. You write f inverse of x. So really similar to this notation, just throw in the little negative 1 for the inverse. Okay, so that's my inverse function. I'm going to sneak a little graph over here. So if I graph the original, this is in slope-intercept form, so my y-intercept is 1, so I can start there, and then my slope is negative 1/2. So I can go down 1, over to the right 2, and plot another point. And 2 lines or 2 points is enough just to get a general picture of what the graph is going to look like. So this is f. This is my original function right here. And then I can plot the inverse based on this. So plus 2, that means my y-intercept is 2. So I can start right there. And then my slope is a negative 2. So I can go down 2, over to the right 1. And then same thing, these 2 points right here. That's enough to show what my line is going to look like. Okay, so this right here is my inverse function. And you can see if we were to sketch this little dotted line in here, the black line and the red line are reflected over that line. Like this piece is reflected over here, this piece is reflected over here, all around that line. Okay, last one. Same thing. First of all, write this in terms of y, because I know the f of x is a little strange. First step is we literally exchange the x and y. So write an x here instead of a y, write a y here instead of an x, and then do whatever we need to do to solve for y. So the first thing we need to do is divide by 3. What I'm going to do is I'm going to multiply by 1/3 instead. Okay, so these will cancel out. 1/3 times 3 is just 1. So I will have a 1/3 x over here equals, and then I'll have a y squared. Okay, so last thing is I'm going to square root both sides here, because what will happen is the square and the square root will cancel out. So I'll have y by itself, and then I have the square root of 1/3 x. Okay, so rewrite f inverse, we're going to write it in that notation. This is the square root of 1/3 times x. All right, so that's what we're working with there. We're going to do a quick sketch. The parabolas we should know how to graph. This one goes right through the origin. There's no vertex change. And then remember the 3 means you can go up 3 units over to the right 1. It'll make it narrow, and then we can mirror that point. So here's our original. We just practiced a couple chapters ago graphing those parabolas. And then we've got the square root functions. And the square root functions we just did. So that the 1/3 x means that we've got a nice stretch of 1/3. All right, so we can stretch it out that way. It'll make it kind of low to the x-axis like that. Okay, so that is our inverse function. Again, you can see the reflection over this line. You can see this piece gets reflected here. Okay, so in that last video we worked through how to find the inverses. You're given a function. We had this whole swap x and y formula. So in the second video, and this is going to be pretty quick, we're going to learn how to determine if we give you two functions, like say I give you an f of x and a g of x, we're going to be able to determine, yes, they are inverses of each other, or no, they're not. So here's how it works, and it's pretty simple. It cuts back to what we did a couple sections ago with composition of functions. So it says two functions, f and g, are inverses if and only if this is true. If we compose f with g of x, meaning if we plug g of x into f of x, and if we plug f of x into g of x, they both come out to equal x. So I've got like a three-piece equality here because they're saying they're both equal to the same thing, they're equal to x. So if I plug g into f, I should end up getting x. If I plug f into g, I should end up getting x. You should test both of them just to confirm that they both come out to be x. Okay, so I've got just one example to look at. Like I said, we're just trying to figure out if these are in fact inverses of each other. So we're going to do f of g of x and g of f of x. So let's start with f of g of x. Okay, so remember, f of g of x means we are going to go into our function f, and every time we see an x, we're going to replace it with g of x. Okay, so I'm going to do some color coding here for you. So 3/4, instead of the x, I'm going to sub in g of x. I guess I should probably put that in parentheses. And then minus 6. All right, so it was exactly the same as this function used to be right here, except I replaced the x with a g of x. Okay, that's all this means. If there was a 3 here, you'd replace the x with a 3. So we've got equals 3/4, and then what I'm going to do is I'm going to sub in the actual function for g of x, which is right up above. So sub that in, and then I have minus 6. So now do whatever we need to do to clean up. We'll simplify it up as much as we can. If it turns out to be x, we're in a good place. So we've got 3/4 times 4/3 x. Notice these 4's will cancel, the 3's will cancel. All I have left is the x, which is a good thing. 3/4 times 8. If I picture this as like 8 over 1, I have 3 times 8, which is 24 over 4. And 24 over 4 reduces down to 6. And then I have minus 6. And look at that. Just what I was hoping for here, I get x. So that's a good start. But remember, just because this one gives me x doesn't mean the other one will. So I've got to test the other one as well. If this doesn't give you x, then you can stop, because they both have to be x. So if one of them turns out not to be x, you may as well just stop there. Okay, so now I'm going to go into my function g, which is this one right here, and replace the x with an f of x. So I have 4/3, and then in place of the x, I'm going to plug in f of x plus 8. Okay, so I'm right in this function here. Instead of the x, what I did is I replaced the x with my function f of x. So let's see how that turns out. So I've got 4/3. And then in parentheses, I'm going to sub in my expression for f of x. Okay, and plus 8 on the end. So just like I did up above, I'm going to clean this up, see what I get. 4/3 times 3/4, just like it did up above, will cancel out. All I have left is the x. And once again, I can think of that as 6 over 1. So I have 4 times negative 6, which is negative 24, over 3, which is negative 8. Plus 8, and these will cancel out, and I end up just with x. So my answer would be yes, they are inverses of each other. And when it says explain your reasoning, we could say yes, and that's because f of g of x came out to be x, and g of f of x came out to be x. When they both come out to be x, that means they are in fact inverses of each other.